This is the second half of the Chapter 9 slides, going over some examples of one-sample hypothesis testing. We begin by discussing the types of possible errors that you can make when you do hypothesis testing. Hypothesis tests never prove or disprove anything, with 100% certainty. When we do hypothesis testing, we're just looking at evidence and we're deciding how much evidence we need to make a conclusion. Two types of errors you can make are type 1 error and type 2 error. Type 1 error is when we reject a null hypothesis, but that null hypothesis is actually true. And type 2 error is when we fail to reject the null hypothesis, and the null hypothesis is actually false. The probability of type 1 error is alpha, or the level of significance we've chosen for our test. So if we do a hypothesis test at the 5% or the 0.05 level, we're also saying that we have a 5% chance of making a type 1 error. The probability of a type 2 error is beta, and we're not going to get into how to calculate that in this class. So this table shows the four possible outcomes when you do a hypothesis test. You either do not reject the null hypothesis or you reject the null hypothesis. And the null hypothesis is either true or false. If it's true and you don't reject it, you haven't made an error. The probability of that occurring is 1 minus alpha. If the null hypothesis is false and you do reject it, again, you haven't made an error. The probability of that occurring is called the power of the test, or 1 minus beta. A type 1 error is when the null hypothesis is actually true, but you reject it in your test. The probability of this occurring is alpha. And a type 2 error is when the null hypothesis is false, but you fail to reject it with your test. And the probability of this type of error is called beta. A few more vocabulary terms. The confidence coefficient, 1 minus alpha, is the probability of not rejecting the null hypothesis when it's true. So again, another way of saying that is the confidence coefficient is the probability of not making a type 1 error. The confidence level of the hypothesis test is just that confidence coefficient expressed as a percentage. The power of a statistical test, 1 minus beta, is the probability of rejecting the null hypothesis when it's false. So again, that's just the probability of not making a type 2 error. Type 1 and type 2 errors can't happen at the same time, because a type 1 error, rejecting a true null hypothesis, can only occur if the null hypothesis is true. A type 2 error, failing to reject a false null hypothesis, can only occur when the null hypothesis is false. Their probabilities move in opposite directions. As the probability of a type 1 error goes up, the probability of a type 2 error goes down. This slide shows a few other factors affecting the probability of a type 2 error. All else being equal, the larger the difference between the hypothesized parameter and its actual true value, the more probability of making a type 2 error. So in other words, as the difference between the hypothesized parameter and its true value goes down, the closer the hypothesized parameter is to its true value, the greater the probability of a type 2 error. Also, the lower you set alpha, the greater the probability of a type 2 error. The larger the standard deviation in the population, the greater the probability of a type 2 error. And the smaller your sample, the greater the probability of type 2 error. The only two that the researcher has any control over are what he or she sets alpha at and how large the sample size is. So you can see from this, the bigger the sample size you have, the less probability you have of making a type 2 error. Okay, so let's talk about hypothesis testing for a population mean when we do not know the population standard deviation. This is by far the most common situation. Most of the time when you're testing a population mean, you don't know the population standard deviation. So when the population standard deviation is unknown, you use the sample standard deviation in its place. Because of this change, you have to use the t-distribution for your test instead of the z-distribution. When using the t-distribution, there's an assumption that must be true. You must assume that the population you're sampling from follows a normal distribution. So for your results to be valid, the population you're sampling from has to be approximately normally distributed. Everything else is the same as what we've already seen. So because you use the t-distribution, this type of hypothesis test is called a t-test. So now we've talked about two kinds of hypothesis tests for the population mean. If we know the population standard deviation, we do a z-test. If we don't know the population standard deviation, we have to do a t-test. And the test statistic is now a sample mean minus the hypothesized population mean divided by the sample standard deviation divided by the square root of the sample size. So here's an example of a two-tailed t-test for the population mean. The claim is that the average cost of a hotel room in New York is $168 per night. To determine if this claim is true, a random sample of 25 hotels is taken, and that resulted in a sample mean of $172.50 per night and a sample standard deviation of $15.40. Test the appropriate hypotheses at alpha equals 0.05. So when we set alpha to 0.05, we're saying we only want to have a 5% chance of making a type 1 error. So we only want to have a 5% chance of rejecting a true null hypothesis. Since the claim we're trying to test has an is in it, the average cost of the hotel is $168 per night. Is like equals. Equals always has to go in the null hypothesis, so we set the null hypothesis to the population mean equals 168. The alternative hypothesis is the logical opposite of the null hypothesis, so it has to be the population mean does not equal 168. So how do we do the test? The first way we can do it is with the critical value approach. We want to find out what are the two values in a t-distribution with 24 degrees of freedom that 5% of the distribution is outside of. Now what's this degrees of freedom thing? The t-distribution is actually a set of distributions defined by their degrees of freedom. The degrees of freedom is just the sample size minus 1. So if you're taking samples of size 2 or size 4 or size 6, each of those will give you a different t-distribution. So whenever we talk about the t-distribution or do calculations, we have to specify what the degrees of freedom is. And again, it's always the sample size minus 1. So these two critical values, if you're calculating them in Excel, it would just be equals t.inv, so the inverse t-distribution, and then in the parentheses you'd have 0.025, comma, 24. 0.025 because you want to find the t-value in a t-distribution with 24 degrees of freedom that 2.5% of the distribution is less than. This critical value is the value from a t-distribution with 24 degrees of freedom that only 2.5% of the distribution is more than. That means 97.5% of the distribution is less than. So it's equals t.inv, and then within the parentheses you'd have 0.975, comma, 24. Then you calculate your t statistic. And this all comes from the values that are given, the sample mean, the hypothesized population mean, sample standard deviation, and the sample size. And you get 1.46. 1.46 is not outside of the critical values, so we do not reject the null hypothesis. So we have insufficient evidence to conclude that the population mean is not equal to 168. So that supports the idea that the population mean is 168. Again, there is an assumption when we do a t-test. We have to assume that the population is normally distributed. But the t-test is fairly robust to this assumption. That means as long as the sample size is not very small, and if the population is not highly skewed, the t-test can be used. So as a general guideline, if your sample size is 30 or more, you should be okay. But another way to see if this assumption is met is to look at your sample. If your sample looks close to being normally distributed, that means that the population is probably also normally distributed. How do we check the normality of the sample? Well, we can do things like do a normal probability plot, or a histogram, or check to see how closely the sample statistics match the normal distribution's theoretical properties. Let's talk about one-tailed tests. Okay, in many cases, the alternative hypothesis focuses on a particular direction. So if the null hypothesis is a greater than or equal to or a less than or equal to hypothesis, that means the alternative has to be either a less than or a greater than. When the alternative hypothesis has a straight less than or greater than sign, then you do a one-tailed test. Because think of it this way, if the null hypothesis is that the population mean is greater than or equal to a certain value, like 3, we can only reject that null hypothesis in the lower tail if we have strong evidence that the mean is actually less than 3. Because with the greater than or equal to, less than is the only thing that can contradict it. If we have a null hypothesis with a less than or equal to sign, we can only reject in the upper tail of the distribution, because the only way we can reject a claim of less than or equal to is if we have sufficient evidence that the population mean is actually greater than some particular value. So here's an example of a lower tailed test. If the null hypothesis is that the mean is greater than or equal to 3, the only place we can find evidence to reject that is if we find strong evidence that the mean is less than 3, and that happens down here in the lower tail. So we only have one critical value in a lower tailed test and an upper tailed test. Similarly, here's an upper tailed test. If the null hypothesis is that the population mean is less than or equal to some value, we can only reject if we have strong evidence that the mean is actually greater than, and that comes up here in the upper tail. So again, we only have one critical value. So here's an example of an upper tail t-test for a mean. A phone industry manager thinks that the monthly cell phone bills have increased and now average over the old average of $52 per month. So the company wants to test that claim. So the claim is that have increased, that the average is greater than $52 per month. A straight greater than sign can only go in the alternative hypothesis, right? Because we learned before that the null hypothesis has to have an equal to. So in this case, the alternative hypothesis is the population mean is greater than 52. That means the null hypothesis has to be the population mean is less than or equal to 52. Because remember, together, the null hypothesis and the alternative hypothesis have to cover all possibilities. So we have our hypotheses there. If you choose an alpha of 0.10 for the significance level, then we need to find the critical value in Excel. So remember, we don't know the population standard deviation, so we're going to use a t-distribution. Our sample size is 25, so the degrees of freedom is 24. So to find the critical value, we need to find the value in a t-distribution with 24 degrees of freedom that 10% of the distribution is greater than. If 10% of the distribution is greater than, that means 90% of the distribution is less than. So we'd use equals t.inv and in the parentheses 0.90, 24. And that gives us 1.318. So now we know we'll reject the null hypothesis if our test statistic is greater than 1.318. So next we calculate the test statistic, which is just plugging all our inputs into this formula here, and we get 0.55. 0.55 is not greater than the critical value, so we failed to reject the null hypothesis. That means we do reject the alternative hypothesis. So we have insufficient evidence that the mean bill has increased and is now over $52. How would we do this same test using the p-value approach? Well, we'd calculate the p-value and compare it to alpha. So remember, our test statistic we calculated is 0.55. For the p-value, we want to find what's the probability of getting a test statistic of 0.55 or greater, assuming that the null hypothesis is true. In other words, in a t-distribution with 24 degrees of freedom, what's the probability of getting a number greater than 0.55? For that, we would use this formula here. 1 minus t dot dist, and in the parentheses 0.55, 24, true. That's because this t dot dist formula tells us the probability of being less than 0.55. To get the probability of being greater than 0.55, we have to subtract this probability from 1. And we end up with 0.2937. So we fail to reject the null hypothesis because the p-value is greater than alpha, which we had set at 0.10. You can also do a hypothesis test for proportions. Proportions involve categorical variables. Those are variables that have two possible outcomes. The population proportion is denoted by pi. The sample proportion is denoted by small p. When both n times pi and n times 1 minus pi are at least 5, we can do a z-test, because then p, the sample proportion, can be approximated by a normal distribution with a known mean and standard deviation, and those are the formulas for them down below. So here's an example. First, the z-statistic is the sample proportion minus the hypothesized population proportion divided by this big square root of population proportion times 1 minus population proportion divided by the sample size. So here's the example. A marketing company claims that it receives 8% responses from its mailing. To test this claim, a random sample of 500 were surveyed with 25 responses. So 25 out of 500 is the proportion that responded, right? That's the sample proportion. The population proportion that's claimed is 8%. So first we have to do our test to see if we can use a z-test. We check to see if n pi and n times 1 minus pi are both greater than or equal to 5. N is 500 because that's the sample size. Pi is 0.08. That means 1 minus pi is 0.92. 40 and 460 are both greater than 5, so we can use the z-test. So the next thing we do is we calculate the z-statistic, which is shown in this box here under the test statistic. We just plug our inputs into the formula and we get negative 2.47. Well, our critical values, if we set alpha to 0.05, we would look at the standard normal distribution or the z-distribution, and find the values, the critical values, that 5% of the distribution is outside of, and we get negative 1.96 and 1.96. If you wanted to calculate those in Excel, it's these two formulas. The lower critical value is equal norm.s.inv with 0.025 in the parentheses, and the upper is norm.s.inv with 0.975. Since our test statistic of negative 2.47 is outside, it's lower than our lower critical value, so we reject the null hypothesis and claim that And that means we reject the claim that the population proportion is 0.08. If we were using a p-value approach, we'd take that z-statistic of negative 2.47 and calculate what's the probability of being that far or farther from the mean of the sampling distribution of the test statistic. So in other words, what's the probability of being less than negative 2.47 and more than 2.47? And we get 0.0136. 0.0136 is less than our chosen significance level of 0.05, so we reject the null hypothesis. How would you find this 0.0068 with Excel? You're looking for the probability of being less than negative 2.47 in a standard normal distribution. So it would be equals norm.s.dist, and then the parentheses you'd have negative 2.47, comma, true. And that would give you 0.0068.